Okay, this is question number 4 from the 2012 AP Physics B exam, and it is primarily a thermodynamics problem. We've got a cylindrical container fitted with a frictionless piston that's initially locked in place. The container has a fixed amount of gas initially at room temperature and atmospheric pressure. We're going to take that cylinder, place it in a hot water bath, and then on the axis below we want to graph the pressure versus temperature for the process the gas undergoes as a result, and then indicate the direction of that process in the graph. So if we think about this carefully, we've got our container that's got a gas in it, right? And a piston that's locked into place here. That, when we unlock it, possibly will go up and down, but right now it's locked in. We're going to take this whole thing, we're going to put it in a hot water bath, which is basically applying heat to it. We're going to allow heat to flow in. And so as heat goes into the gas, the piston is not able to move, so the gas can't do any work. So we get a situation, if we look at the thermodynamics equation of U equals Q minus W, and be careful, this minus is referring to by the gas instead of on the gas. We got to see here that W is 0, so the internal energy will change or equal. That change in internal energy will equal the heat that we add. So by adding heat, internal energy will go up, which will end up resulting in the temperature changing because we're not going to change the amount of gas. So delta T will increase. It's a linear relationship. There are no exponents, radicals, or anything like that in here. So internal energy will rise linearly with the heat. We also have to, so we understand how temperature will rise, but now we've got to understand what's happening in the pressure. We'll think about this. The gas is going to have much more internal energy, so it's going to be pushing out in that wall a lot more than it wanted to before. So its internal pressure will also rise. And the last thing I just want to point out is it's going to rise at the same rate as the temperature, because we got to look at that ideal gas equation relationship. And again, the volumes are constant. It's a 2 here. The volumes are constant. The piston's not allowed to move. And so the relationship of P1 to T1 has to be retained. So if the second temperature is higher, then the second pressure needs to be equally higher. So we're basically looking at a 45-degree slope. And it doesn't indicate exactly where it needs to begin. So I don't think it does. No. So I'm just going to take a line, and I'm going to create a 45-degree slope rising with the temperature and pressure, and I'm going to indicate the direction of the process with the arrowhead. A was worth 3 points. You get the point for showing the relationship for pressure and temperature are proportional. You get a point for ending higher pressure and temperature than where you started, and you get a point showing that that initial temperature and pressure are not 0. And that's important to see because it says it's originally at room temperature and atmospheric pressure, so we certainly couldn't start at the origin. Now the cylinder is removed from the hot water bath, and after equilibrium is reached, the lock is removed so the piston is free to move. We want to know, does the piston move up or down or stay the same? And so let's kind of look at this situation down here. I'm going to remove that heat because it's out of the bath. And what's going to happen to this piston once we unlock it? Well, originally, the pressure inside this container was atmospheric pressure. Once we remove that heat, it's going to go back to being atmospheric pressure. And there is atmospheric pressure above the container, but they won't equalize completely because we also have this downward pressure being exerted on the gas from the mass itself. And so the lock will go down because it's applying pressure on that gas and it's going to compress it into a smaller space. It's going to move down, and again, justifying it, I would just basically indicate that the mass itself is pulled down by the force due to gravity, and that causes it to fall a little bit. And B was worth 2 points, 1 for indicating it moving down, and then 2 for legitimate justification. So now, when the system is again at equilibrium, the piston is pushed down very slowly. So I'm going to go ahead and grab that piston again. It's pushed down very slowly, and we want to sketch the pressure versus volume as a result of this. Now, when it's getting pushed down very slowly, what it basically is implying is the work that we're doing on the gas is going to be released in the form of heat at the exact same rate. It's going slow enough that any internal energy that wants to rise up won't, because the heat is leaking out. Basically, the internal energy of the gas stays the same. As a result, when we know the volume is going to decrease, and we know what it had to because we're squeezing it down, and we know the pressure's got to increase. The internal energy, as I just said, is going to stay the same, so there will be no delta U. Remember, U is proportional to temperature. If we look at that 3/2 nRT equaling U equation, your N and your R are constant, so U and T are directly proportional. Since there's no change in internal energy, there's no change in temperature. So as the volume decreases, the pressure will increase, and it will all do this isothermally. So we should see an isothermal curve, and it's going in that process because it's decreasing in volume and increasing in pressure. I'm going to go ahead and label this process C. We're then going to take that piston and we're going to pull it up really quickly. And so it's kind of the opposite is true. By pulling it up quickly, we are not allowing the heat to enter the container or leave, but in this case it wants to enter. We're not going to allow the heat from the environment to enter the container really at all because it's happening so fast. So we're I have to grab my mouse here. We're expanding this piston, so we're pulling the gas into a larger space, but we're not allowing heat to flow. So internal energy will change in this example. And so we do need to finish at a larger volume. There's going to be much less pressure than the prior state because it's taking up more space, and it is not going to be isothermal. In fact, what's going to end up happening is it's going to be adiabatic. No heat will be able to flow in or out of the system. An adiabat looks a lot like an isotherm, but it's going to be steeper. And you know it needs to be steeper because it's not going to be isothermal. And that's going to be process D. This entire graph is worth 5 points. You get a point for having the curve for C being indicated correctly, the one for D indicated correctly, indicating that the final state of curve C and the initial state of curve D are the only spot where they intersect, so having them intersecting up here, you get that point. You get another point for drawing C above D and not below D, and then finally you get it for labeling and giving proper direction to the process. So if you understand your thermodynamics, this was a gimme because it's worth 5 whole points right here. And that's it for number 4.